Alright, continuing with 6 to 7, today we are doing an introduction to perturbation methods. These are based on asymptotic expansions. So let me give you an example. Just first think of something simple. X plus 3, x plus 5 equals 0. That means x is equal to minus 3 minus 5. But let me write this as x squared plus 8x plus 15 equals 0. These are the roots. Okay, this is a known problem. Known, solvable, easy, whatever. This is a simple problem. Now let epsilon be greater than 0 and much less than 1. Okay, so we will develop based on small epsilon asymptotics. We will use small epsilon asymptotics. Okay, so let the new equation be epsilon x to the power 4 plus x squared plus 8x plus 15 equals 0. Now this has 4 roots. Since epsilon is small, 2 roots are close to the old roots. Let's try those first. Those are 2 of these roots are slightly perturbed versions of minus 3 and minus 5. Okay, alright. It's better to proceed vertically. Let's proceed vertically. So what we do here is we pose an expansion. Okay, now actually we may be interested in epsilon equals 0.1 or epsilon equals 0.003, some specific epsilon. But in this expansion we want it to work for all epsilon sufficiently small. All epsilon sufficiently small. Okay, that is what we will want it to work for. So minus 3 is one of these roots. So let me try a root of the form x equals minus 3 plus a1 epsilon plus a2 epsilon square plus a3 epsilon cube plus dot dot dot. It may well turn out that for some epsilon, like this epsilon maybe, it may turn out that the series is not convergent. However, we are not relying on that. What we are saying is that for epsilon sufficiently small, the series will be good if it is an asymptotic series, and it is clear that this form is asymptotic. Okay, so for any fixed number, maybe this is 1 and maybe this is 10 and maybe this is 10,000, but the series is still asymptotic. 1, 10 and 10,000 will remain fixed, and as epsilon goes smaller and smaller and smaller and smaller, eventually this will be much smaller than this, and this will be much smaller than this, and so on. Okay, so that's how the series will work. This series, let me call it XA. I will substitute here. So this I am writing as f of x comma epsilon equal to 0, right? Then when I notice that f of minus 3, 0 is equal to 0, right? So minus 3 is a solution. Then I try f of xa epsilon equals 0. So I have substituted the series, And then what I do is I take this quantity, reddish one, let me take this quantity here, and I expand it out, and I have f0 plus f1 epsilon plus f2 epsilon square plus dot dot dot, and I want that to be 0. Now because I have started the series with the correct value, this is going to be 0, and I will insist that this has to be 0, this has to be 0, and so on, and I'll get a system of equations, and I will solve that system for the unknowns a1, a2, a3. Okay, so that is how this method works. Let me show you the calculation in Maple. Okay, so here I am. I will say EQ equals epsilon times x to the power 4 plus x plus 3 times x plus 5. Okay, this is the thing that is going to be 0. Okay, now I can say solve EQ for x, and it will either not do it or it will give me some terrible expression. So in this case it's not doing it. However, I can say eval f solve substitute epsilon equals 0.1 in EQ x, and now what it will do is it will substitute epsilon equals 0.01 in this equation, then it will solve that and give me numerical solution. So it should give me 4 roots. Okay, and here they are. So here is a complex root, here is another complex root, here is another complex root, here is another complex root. I've got 4 complex roots, so that's not very good. It is not close to -3. Okay, so let me try 0.02, and now what do I have now? Now I have 3 plus something big, -3 plus something big, -3 and a small number. Okay, so this, how about 0.002? Okay, very good. Now I have this complex root, this complex root, here is a root close to -3, and here is a root close to -5. Okay, but it has moved quite rapidly. Okay, so let us persist with this problem and see how it goes. So we will say xa is equal to -3. Let me try one thing here. Let me say n equals 4. Okay, x -3 plus add a k times epsilon to the power k, k equals 1 to n. That's my approximation. I want to find a1, a2, a3 and a4. Then I will say EQA is equal to expand substitute x equals xa in EQ. This will give a terribly long expression. Okay, so that is because it has got all those powers, epsilon to the power 11 and so on, which we have no reason to keep because we have kept terms only up to epsilon to the power 4. And so what I will do is I will say convert Taylor, and then over here I will say for small epsilon, and I will say n plus 1, and I will say polynomial. Okay, so now it will give me a smaller expression, and you see the order 1 term is missing. Like I said here, this one is missing. You see, this one is missing. Okay, so there is something that is order epsilon, something that is order epsilon square, something that is order epsilon cube, and something that is order epsilon to the power 4. The nice thing that you will notice is that you see this thing is going to be 0, right, this coefficient, and it's non-linear. But this part being 0 gives me a linear equation in A1. Once I know A1, this one being 0 A1 appears non-linearly, but it is a linear equation in A2, so I have A2. When I set this equal to 0, A1 appears non-linearly with A2, but A3 appears linearly, and over here A4 appears linearly. Okay, so I come here now and I say solve, and I say the sequence of the coefficient in EQA epsilon k equals 1 to n. Solve it for the sequence of k equals 1 to n. Okay, and you can see this is why that was not working very well. This coefficient is very big compared to this one, and this is big compared probably to this one, and this is big compared to this one. This is why there is a problem with this series, but it is an asymptotic series. Okay, and so I will come here and I will say, where is my approximation? XA. So I will say XA is equal to, substitute the previous in XA. This is my series. It is a truncated series. There are more terms over there. After this there are other terms. I have truncated it, but it is an asymptotic series. Okay, so now let me come here, let me put 0.002. So for example, eval f, substitute epsilon equals 0.002 in in XA. And you see I get minus 3.0963. Here I had minus 3.096. You see, so the difference from 3 is captured quite accurately. Okay, what is the error? The error, let me take the error. Okay, so let me take this one here, and I'll say EE is equal to that minus the previous. Okay, so this is the error. Okay, remember that this is the error. Now let's come here and try epsilon half of that. Okay, so now I have some other value. Now if I come here, here I try epsilon half of that, that root will also change. It will get closer to 3. Okay, so that's what the root is. Now let me come here and say EE2 is equal to this one minus the previous. Okay, oh, that didn't work. That's because I have to run it again. Okay, so now here is this error. Okay, here was the previous error, here is the new error. Okay, there is an epsilon to the power 5 term here, you see. So now when I come here, I've divided epsilon by 2, so something like 2 to the power 5 times is how much smaller the error needs to be. We can do that. We can take this one, Control C, Control V, divided by with a minus, well, even the minus is not needed, I guess. Here, Control C, Control V, and you see it was supposed to be about 32 times, it's about 39 times, right? So that's, when you take epsilon even smaller, it'll get better. Okay, so that's how much smaller the error is. This is because it's an asymptotic series. As you take epsilon smaller and smaller and smaller, eventually it starts working extremely well. Over here, you know, I was saying it may or may not work for the specific epsilon you have in mind, but there is an epsilon below which it will begin to work really well. This is because it's an asymptotic series. Okay, so that's the first part. What about the other roots? So for minus 5 also there is a similar root. I can work it out and show you. So I can come here once again and I can just restart, it doesn't matter. It doesn't matter. Here, minus 5. Okay, So that's the new series. You see now I'm posing around -5, so I'll get a different series, and this series I will solve, and you see this coefficient is even bigger. It's a terribly large coefficient, but it's okay, that's what it is. Then we come here, and over here I think we have to put 1 and get rid of that. And you see now here we had -4.712, and here we have -4.712. Okay, so that's how this asymptotic series works. We've got two roots which are close to the original roots. We've got two roots which are perturbations of these roots. Okay, so this part is done. What about the other two roots? Now if you think about it, you'll realize that epsilon x to the power 4 plus x square plus 8x plus 15 equals 0 if epsilon is small and x is order 1, then this is a perturbation of a quadratic equation, and we have two roots. Why do we think there are 4 roots? Because although epsilon is small, the introduction of this term has made it a 4th order polynomial. And so it is only when this term is felt in the equation, when it has weight, that we will sense the other roots. How will this have weight? How will this equation become a player? How will this term become a player in the equation? If epsilon is small, the solution is that x has to be big. Okay, so we will need x to be big. How big? Well, if x is big, then this term is bigger than this one and this one. And so, to see how big x needs to be, we balance epsilon x to the power 4 plus x square equals 0. We set it equal to 0. We know it's not exactly 0, but we just want to see how big x is. Okay, and this means epsilon x square plus 1 is equal to 0. That means x is order of 1 by square root of epsilon. I hope that part is clear. Okay, so now if x is order 1 by square root of epsilon, in that case we will say, let me find where is my cursor. So epsilon x to the power 4 plus x squared plus 8x plus 15 equals 0. Let us say let x be equal to y by square root of epsilon. So now y is order 1. Okay, as epsilon goes to 0, x goes to infinity, but y goes to some fixed quantity. This is an ansatz, this is a guess. This is an assumption about the form of the answer. Okay, so when we do that, then we find epsilon y to the power 4 by y epsilon square plus y square by epsilon plus 8y by square root of epsilon plus 15 is equal to 0. We multiply by epsilon, and so we have y to the power 4 plus y square plus 8 square root of epsilon y plus 15 epsilon equals 0. Okay, now let us say delta equals square root of epsilon. So y to the power 4 plus y square plus 8 delta y plus 15 delta square equals 0. Set delta equals 0, we have y square plus 1 equals 0, so y is equal to plus minus I, and so now we will pose a complex series. So we will take this equation here, we will say y to the power 4 plus y square, this equation here, plus 8 delta y plus 15 delta square equals 0. Y is equal to I plus a1 delta plus a2 delta square plus a3 delta cube and so on, and then we will see what happens. Okay, so let's go back to Maple and we say EQB is equal to, substitute x equals y by square root of epsilon in EQ. Okay, so that's what that is, and then we say now YA is equal to I plus add AK. Oh, wait. So now let me say EQB is equal to, substitute well here let me see, SQRT epsilon equals delta EQB. Well, that didn't work. Let me just write it separately instead of fighting with it. Okay, so here we will go EQB is equal to y to the power 4 plus y square plus 8 delta y, 8 times delta times y plus 15 times delta square. This is what is going to be 0. Let me say y approximate solution is equal to I plus add AK times delta to the power k equals 1 to n. I have that. Then I have EQB approximate is equal to, expand, substitute y equals y approximate in EQB. This will be some big long expression. So what I will do is I will say convert Taylor delta n plus 1 polynomial. Okay, all right, now it should be doing this. Oh, I think I have to write capital I. Let's see if that works. Okay, so that took care of the order 1 term. and then over here you see a is real and so on, and delta, delta square, delta cube, delta to the power 4, and then I will say solve the sequence of the coefficient in EQBA of delta to the power k, k equals 1 to n. Solve the sequence of a k, k equals 1 to n. Here it is. This is the answer. Once again you see that these coefficients are increasing rapidly, and in fact you see it's also interesting. One is real, then one is imaginary, then one is real, then one is imaginary. So you have to work with complex arithmetic, but that's all right. Okay, so then what we have is ya is equal to, substitute the previous into ya, and then what we have is x a is equal to, let me see now, substitute delta equals square root of epsilon in y by square root of epsilon, not y but ya. Okay, so this is my approximation. All right, and now we can evaluate this for epsilon equals 0.001, for example. So eval f, substitute epsilon equals 0.001 in xa, and you see I have 3.86 plus 32.1 I. Let's go here, 3.87 or 3.88 plus 32.1 I. This is not bad, and I think you will agree that if I take more terms it may get better, but I will emphasize that these are asymptotic series. They are not guaranteed to be convergent. If you are interested in a certain value of delta, you may find that by taking more and more terms it is not getting better. But what you will find is that if you truncate to a certain number of terms, and if you take delta smaller and smaller, it will get better and better, and with luck you will have a problem where the value of delta that you are interested in, or the value of epsilon that you are interested in, falls in that small enough range so that the solution you get is useful. So this is the first introduction to perturbation methods. We will continue in later lectures.